All right, this is a review of homework 11. So there was one problem from the textbook, and then there were two additional problems that I created. So this one is from the textbook. It said, for each of the following scatter diagrams, indicate whether the pattern is linear, curvilinear, or no correlation. If it's linear, indicate whether it is positive or negative, and the approximate strength, large, moderate, small, of the correlation. So here's the first two figures. Figure A is no correlation because there is no pattern of highs going with highs and lows going with lows, or with highs going with lows. We've got highs going with lows and lows going with highs and lows going with lows, so no discernible pattern. We've got no correlation there. B, we certainly have a curvilinear correlation because we see that we have a bend or a curve, so curvilinear. C, we have I said a moderately strong positive correlation. Certainly is positive because we have the general trend of the scatter plot sloping up as we move from left to right. So again, highs going with highs, lows going with lows, moderates going with moderates. And in terms of evaluating whether it's small, moderate, or weak, strong, moderate, or weak, we're really looking at the extent to which these dots cluster around a straight line. So if we're kind of to eyeball a line of best fit through those dots, we're making a judgment as to whether they're landing on that straight line. Here's a good example of a very strong correlation where we have each of those observations almost falling perfectly on a straight line. So here we've got a very strong negative correlation. This is not a perfect -1, but it's very close, probably like a negative 0.95 or something like that. And of course it's negative because we've got the dots sloping down from left to right. So in this case, high scores on the X value are going with low scores on the Y, and low scores on the X value are going with high scores on the Y, moderates going with moderates. E, no correlation for the same reason. And then with F, we've got a strong positive correlation. All right, problem 1 that I created, there's actually 3 parts to it. And so I said for each of the following sets of data, first thing, make a scatter diagram of the scores. B, describe in words the general pattern of the correlation. C, figure the correlation coefficient and show the work. I really stress that in doing your calculations, you use this definitional formula. There are other formulas that you can use. You will get the correct answer. But the point in this class is to have you understand the conceptual reasons behind the statistics. And so what we have here is more or less a definitional formula. This is a formula that provides a definition of what a correlation coefficient is. So it really kind of shows you how and why the numbers are what they are. So you can plug in numbers into anything that you want, but this will allow you to understand where and why the numbers are what they are. So here's the first problem. As you're looking at the data, you should look at it and say, okay, here's my X scores, here's my Y scores. It looks like there's an exact 1-to-1 correspondence between our X and the Y. And indeed, when you plot those in a scatter diagram, you can see that they fall in this exact straight line pattern. So this is a perfect positive linear correlation, and when we calculate the correlation coefficient, we should arrive at +1, exactly +1 as the answer. Maybe in calculating it, you've got some small rounding errors or something like that, but you should know that when you calculate it, you should get a +1. Okay, so here's the numbers. Again, I like to arrange my calculations in this table format. This is just so I can really see where all the numbers are coming from that are contributing to all the intermediate calculations and then the final calculations. But what we have to do, I didn't provide the formula, but maybe it's right here. There it is. what we have to do to use this formula is we've got to transform our X score to a Z score, and we've got to do that same thing with our Y score. Okay. Once we transform each of our raw X scores into a Z score, and once we transform each of our raw Y scores into a Z score, we multiply those Z scores together. Okay, so this is our cross product of X and Y. Okay, so we got 1.8 by just multiplying negative 1.34 and negative 1.34. We got 0.2 by multiplying negative 0.45 and negative 0.45. What we then do is we take the sum of those cross products and then we divide by the number of sets of scores, we could say. Okay, so like the number of participants. So when dividing the sum of the cross products by 4, we get a perfect correlation of 4. And then what I really like to do is I've created the quadrants, so these lines are plotted at the mean of X and the mean of Y. And again, you can see if we go back to each of the cross products, we can see that for the numbers 30 and 40, okay, so being above the mean on both, we've got positive cross products that are found here and here. This is the 0.2, this is the 1.8. For being below the mean on both X and Y, so being at 10 and 10 and 20 and 20, so right here being at 10 and 10 and 20 and 20, we also get positive cross products, right? So that's our positive cross product of 0.2 and of 1.8. Why are these positive cross products? Because we've got negative Z scores for both. Okay, so being below the mean on X and below the mean on Y results in a negative Z score for X and a negative Z score for Y. But when we then multiply those negative Z scores together, we get a positive cross product. So that's really, it's why I think that this is such a useful and intuitive formula, is to really say, oh, that's how we're doing it. Okay, that's how Carl Pearson, the person that invented the statistic, said, this is how we are going to express a positive relationship, that if we capture the cross products, because we know if you're above the mean, in other words, you've got high scores, we're always going to get, on both, you're going to get positive cross products, but you'll also get positive cross products if you're below the mean on both. Therefore, when we sum those together, on balance, we're going to get positive cross products. We could say on average. This problem, the numbers are very similar, but you can just see that there's an exact one-to-one inverse relationship between X and Y. Okay, and so when plotted, we get a perfect negative linear correlation. And when you really didn't have to do any new calculations for X. For Y, it's pretty much the same numbers as well. You just have to be careful with the signs. So when multiplying together, you can see that the cross products are all exactly the same as in 1A, but they just turn out to be negative. So when we sum those up, we get a -4, which makes our correlation -1. And again, that makes sense if we think about this adding up or summing up all of our cross products. Here in this quadrant, we're always going to get negative cross products because we've got a negative Z score but a positive Y score, okay, or a negative ZX but a positive ZY. So these are going to create, in this quadrant, always are going to create negative cross products. We're also going to get negative cross products in this quadrant as well because we got a positive ZX but a negative ZY. Okay. And then final example, especially when you plot it, hopefully you were able to see like, hey, there really shouldn't be a correlation here because there's no pattern of either highs go with highs and lows go with lows, or it seems to be that lows are going with highs. We've got, we've got lows going with lows and highs going with lows and highs. So we've got zero correlation. And when we do the calculation, again, I try to keep the numbers pretty easy. You should see that when you take the cross products, all of those cross products are going to sum to 0, which makes the correlation 0. Just putting these in the quadrants or the grids, we can map on our different cross products with each of the points. Okay, so if we go to 10 and 10, that was a cross product of 1. And so we can see that if we go to 10 and 10, we've got a positive cross product. But again, that's just because we've got below the mean on X by 1 standard deviation, below the mean on Y by 1 standard deviation. So if you're below the mean on X and Y, you're going to end up with that positive cross product, which contributes to a positive correlation. Okay? But we've got the positive cross products getting canceled out perfectly by the negative cross products, resulting in 0 correlation. All right, and then the last problem asked, is hours of study significantly correlated with exam scores? So just trying to keep the data simple. These are done mainly for the sake of illustrating how the correlation formula works. In most real-world applications, people are going to use statistics software. But the reason that we do hand calculations in this class is so you can see where the numbers come from. That's the whole point. So we're making a scatter diagram of the scores, describing in words the general pattern of the correlation, figuring out the correlation coefficient, and then determining whether that correlation is statistically significant. And I instructed you to use the 0.05 significance level as well as a two-tailed test. All right, so here's the pattern of data. You can see that generally we have a positive correlation because the trend of the data is sloping up from left to right. Study hours is the X variable and exam score is the Y variable. Why? Because study hours are the amount that you study should predict. It should be the predictor of the outcome, which is exam score. Okay, our same process for calculating the correlation. We convert our X into Z scores. We convert our Y into Z scores. We take the cross products. We sum them up. We divide by the number of people in our study, which is 4, and we get a correlation of 0.87, or close to it. So if you didn't quite get 0.887, it should be about there. And maybe look through some of your intermediate calculations and see if you're off at your sum of squares or variance or standard deviation. And hopefully my numbers are right. I believe that they are, but you can let me know if they're not. So we've got a strong correlation, but we want to ask, is it statistically significant? So the way that we're going to do that is we are going to use our table of t-values to come up with a critical t that we need, and then we're going to convert our correlation to a t, and we're going to compare, once converted to a t-statistic, does our t-statistic exceed the critical value that it needs to in order for us to conclude that it is statistically significant. Okay. So we have 2 degrees of freedom in this case because when figuring a correlation, degrees of freedom is calculated as n minus 2, where we've got the number of participants minus 2. So 4 participants minus 2 is 2. Alpha level 0.05, and then it was specified to do a two-tailed test. Essentially what we're testing here is whether or not the correlation is different from 0. Okay. We're testing whether the correlation that we sampled could be drawn from a population that has a correlation that is either greater than 0 or negative 0. So we didn't make a prediction by doing a two-tailed test. We're saying, hey, it'd be kind of weird, but study hours could be either positively or negatively correlated. In our brain, we probably have the hypothesis that it's positively correlated, but by doing the two-tailed test, what we're strictly testing is whether the correlation could be drawn from either a population in which those variables are positively correlated or one in which they are negatively correlated. So we're accounting for both possibilities. So here's a t-formula. This is not intuitive, whereas the correlation, the formula for calculating the Pearson correlation is intuitive. I think this one really isn't. But I have, the way that I've described it in previous lectures is you can think of the t-formula to calculate the statistical significance of a correlation, just like doing calculating a t-statistic for looking at a difference between means. In the numerator, we've got an effect size. When we did a t-test earlier in the class, the effect size was really the difference between two groups. Here, our effect size is a relationship between two variables. It's a correlation. The bottom of the denominator of the formula is a measure of standard error. So when looking at the difference between two means, a standard error is, well, about how much different would we expect any two means to be if we sampled them from a population. Here, our measure of standard error is, hey, if we just randomly sample 4 people, that's how many people are in our example, if we just randomly sample 4 people, even if we're sampling them from a population in which the correlation truly is 0, about how big might we expect a correlation to be just purely out of randomness, okay? That's basically what the concept of standard error is. It's to say, when we compute a sampling distribution, which is to take all possible samples of size 4, if the null hypothesis is true, most of those sample correlations that we calculate should be 0. Some are going to be more, some are going to be less. Very few of them are going to be big, and either like a strong positive or a strong negative. But if we want to get a sense of in that sampling distribution for any random sample that we could calculate, about how big could we expect a correlation to be just based on sampling error. That's what the denominator of the formula tells you. So what this 0.35 is saying is 0.35 would be like 0.35 would be a standard error. Even if the null is true, based on a sample size 4, it wouldn't be very unusual to just randomly calculate a correlation of 0.35. So the correlation that we're calculating, we're evaluating in terms of how many standard errors is that correlation of 0.87 away from the expected mean of 0. And the answer is, under the null hypothesis, an expected correlation of 0, the correlation that we got is 2.49 standard errors away from that, within some rounding error. So your numbers might be slightly different. Okay, and what did we need? Well, we actually needed our sample correlation to be 4.3 standard errors away, okay? Either in the positive direction or the negative direction. So even though that t looks pretty big, and under other circumstances, if we get a t that is that big, we reject the null. But here, because our sample size is so small, we have a very high critical value. So our t that we calculated does not exceed the critical value. So we do not reject the null hypothesis, okay? The null hypothesis being that the true population correlation rho is 0. So what we would conclude is that despite a strong correlation of 0.87, these data are insufficient to reject the null. We fail to reject the null. And we fail to reject the null that the true correlation in the population is 0. And the reason, of course, is because n is only equal to 4. And so what this is saying is that this correlation, despite looking big, could be due to sampling error or randomness. And that's a really important principle, really for this class and all of statistics, is that sometimes we do a study and we get a result in our sample. It could be a difference between two means. It could be a correlation. And we say to ourselves, oh, wow, there must be something going on. There must truly be a relationship between studying and exam performance. Or there really must be a difference between this group of people and this group of people. But what inferential statistics allows us to do is determine whether that is a reliable difference that would be found among a larger population, or whether that is merely an effect that was due to error or randomness in the small sample that we have. Okay, and so in this case, despite a strong correlation, sure looks like there's an effect, sure looks like there's a relationship between hours of study and exam score. And among these 4 people, no doubt, to be sure, among these 4 people, there is a strong relationship. But that's only among these 4 people. That's not what inferential statistics is. Inferential statistics is saying, is that relationship found among all people, our population? Not just the 4 people that we have in our sample, but in a population. And based on only 4 people, this strong correlation would be insufficient evidence to make a generalization about all people in the population. How big would we need that correlation to be? I presented this in a previous lecture, and I think this is a nice complement to looking at the critical T, because the critical T of plus or minus 4.3 doesn't exactly show you how big the correlation would need to be. So if you transformed that critical T of plus or minus 4.3, you'd come up with basically like a correlation of 0.95. So what we would need is that with only 4 people, when doing a two-tailed test with an alpha level of 0.05, we need a correlation at least as big as positive 0.95 or negative 0.95 in order for us to say, oh, that correlation is far too big to be considered random. Okay. And by the way, this 0.95 has absolutely nothing to do with the alpha level of 0.05 and 0.95. It does, don't get confused about that, okay? But that's what this critical value is saying, is that if we've only got 4 people, we need to see a very, very, very large correlation of either 0.95 or negative 0.95 for us to say, yeah, I know we only have 4 people, but still, just randomly, it would be very, very improbable to get a correlation as big as 0.95 if there's not a positive relationship in the population. I don't know just how big that correlation is in the population, but I can at least say, okay, this is the inference, I can at least say it is improbable, based on 4 people, to get a correlation that is as big as 0.95 if the true population is 0. So I reject that at 0, it must be a positive correlation. I just don't know what it is. Okay, so that's the inference. Anyway, hopefully that was a helpful review, not only of the homework, but some of the other principles from this chapter. If you had any issues with doing the calculations, please go back and look at the calculations that I provide. Make sure to spot your errors. Calculating a correlation coefficient is for sure something that is likely to appear on the exam, so make sure that you're comfortable with it. Do several practice problems. Make sure that you can repeat using that formula, and you're so practiced that you can do it quickly and efficiently.